Hey everyone and welcome to channel. Today we are exploring the world of multiprocessor system. These are the powerhouse of computing handling tons of tasks at once. You ever wonder how your computer juggles so much? A lot of it is thanks to these systems. Let's dive in on this topic. So now see the introduction. So we established that multiprocessor system have multiple processing units, CPUs and IOPs working together. But why do we do this? The main reason are performance and reliability. More processors means more power. They can tackle more tasks simultaneously, making everything faster and more responsive. Plus, if one processor fails, the other can take over, keeping the system up and running. Think of it's like a team working together. More more hands make light work. And if someone's out, the other can still get the job done. In the upcoming slides, explore the different ways of this process. And next, the reason to choose multiprocessor systems. So we know multiprocessor systems have multiple brain working together, but how are they organized? Crucially, they are typically managed by one operating system. Think of the OS as the conductor of an orchestra, ensuring all the processes and other components work together harmoniously to solve the program. The single OS provides the communication pathways and manage the resource, making sure everyone plays their part. Now, one of the biggest advantage of this setup is improved reliability because there are multiple processors. If one of them experience a failure or error, that does not bring the whole system down. The other processor can continue working and the impact of the error is limited. It's like having backup singers. If one loses their voice and the show can still go on. This redundancy makes multiprocessor systems much more robust and dependable, especially for critical applications. Let's talk more about the reliability factor. Imagine one of the processors in our multiprocessor system suddenly fails, maybe due to a hardware issue or software bug. In a well-designed system, this doesn't mean game over because we have other processors available. The operating system can be step in and reassign the tasks that were being handled by the failed processor to one of the others. It's like having a spare tire. You might have a flat, but you can still keep driving. Now, while the system can continue to function, there might be a slight dip in performance. Think of it like this. If one member of your team is out sick, the other can cover their work, but things might be a little slower overall. However, the crucial point is that the system continues to function correctly. This fault tolerance is a huge benefit of multiprocessor system, making them ideal for situations where downtime is unacceptable, like in servers, financial systems, or even space exploration. The operating system's ability to dynamically reallocate tasks is key to maximizing this benefit. In next slide, classification. Now all multiprocessor systems aren't created equal. One of the key ways they differ is in how their memory is organized. This leads to two main classification, shared memory and distributed memory. First, we have shared memory systems, also known as tightly coupled systems. Imagine all the processors having access to one big pool of memory. They can all directly access and thus share the same data. This makes communication between the processor fast and efficient. It's like everyone in a meeting room sharing the same whiteboard. However, managing access to this shared memory can become complex, especially when many processors are trying to access the same data at the same time. Then there are distributed memory systems, also called loosely coupled. In this architecture, each process has its own local memory. They don't directly share memory, instead, they communicate by sending message across a network. Think of it like different teams working in separate office and communicating via mail. This approach is more scalable, meaning you can easily add more processors without creating memory bottlenecks. However, communication between processors is slower compared to shared memory. So the choice between shared and distributed memory depends on the specific application requirements. Shared memory is good for tasks that require frequent and fast communication, while distributed memory is better for large scale systems where scalability is primary concern. Shared memory. There is a global common memory is used in CPUs, and information can shared among the CPUs by placing it in global memory. Next, let's take a closer look at distributed memory system, known as loosely coupled. The key idea here is that each has its own dedicated local memory. Think of it as each person having their own desk and a filling cabinet. They work independently, but they can still communicate. In this system, processors don't directly share memory. Instead, they exchange information through a technique called message passing. Imagine sending a letter. You write the message, address it, and send it. Similarly, distributed memory system, a processor wanting to share data packages it up into a message and sends it through a network to the recipient processor. This network switching scheme is crucial. It's like the postal service routing message from one processor to another. The design of this network greatly impacts the performance of the system because communication happens through message passing. It's generally slower than the direct memory access shared memory system. However, the big advantages of distributed memory is scalability. You can add many more processors without running into memory contention issues, making it suitable for large scale parallel processing. The next is interconnection structures. So let's recap the core components of multiprocessor system. We have the CPUs, the brain of the operation. IOPs, specialized processors handling communication with input-output devices, and the memory unit, which can be organized in different ways. Importantly, this memory can be divided into separate modules. Think of it like having multiple filling cabinets instead of one gained one. It can sometimes improve access speed and organization. Now, how these components are connected is critical. This interconnection between them determines how efficiently they can communicate and share data. In shared memory system, this interconnection focus on providing pathways between the process and the memory modules. The more pathways available, the faster the process can access memory. Think of it like having multiple lanes on the highway. More lanes means less traffic. In distributed memory system, the interconnection is between the processing elements themselves as each has its own local memory. Here, the interconnection network is key for message passing. The design of this network, whether it is a simple bus or more complex network topology, greatly impacts the speed and efficiency of inter-processor communication. So the physical configuration of this interconnection is major factor in determining the overall performance of the multiprocessor system. Next, we see the multiprocessor interconnections. Now, we talked about the importance of the interconnection network in multiprocessor system. Now, let's look at some of the common physical forms of this network can take. There are the different ways processor, memory, and I/O are connected. First one is time shared common bus. This is the simplest approach. All components share a single communication line or bus. Think of it like a one-lane road. Only one transfer can happen at a time, so it can become a bottleneck as the number of processor increases. Next one is multi-port memory. Here, The memory unit has multiple ports, each connected to a processor. This allows several processors to access memory simultaneously, improving performance compared to single bus. It's like having multiple lanes on the road, but all going to the same destination. Next one is cross bus switch. This is one more complex and powerful interconnection. It provides a direct connection between any processor and any memory module. Think of it like a complete network of roads allowing everyone to get where they need to go without traffic jams. However, cross-bus switches becomes very large and expensive as the number of processors increases. Next one is multi-stage switching network. This approach uses multiple stages of switches to connect processors and memory. It offers a compromise between the simplicity of bus and the high performance of the cross bus switch. It's like having a network interconnected highways. The last one is hypercube system. This is more specialized architecture where processors are connected in a multiple dimensional cube-like structure. It offers efficient communication pathways for certain types of parallel algorithm. Each of these interconnection seems has its own advantages and disadvantages in terms of cost, complexity, and performance. This choice of which one to use depends on the specific requirements of multiprocessor system. These are the multiprocessor interconnections. Multiprocessor interconnection. Time shared command bus. I already told that only one processor can communicate with the memory or another processor at a given time. Transfer operations are conducted by the processor that is in control of the bus at the time. Next, mm, multiport memory system. Separate buses between each memory module and the CPU. The advantages of multiport memory is organizing high transfer rate. Mm, Next, cross bus, which a cross bus which organization which supports simultaneous transfer from all memory modules because there is a separate path associated with each module. Multi-stage switching. The basic components of multi-stage network is two input, two output interchange switch. Hypercube. Okay, the topic is ended. So we see in next video. Thank you guys. Bye.